Hi and welcome. I'm trying to learn particle physics. Today, symmetry and a standard model, or symmetry of a standard model. And after we've done it, we're going to do morning stretching. If you participate in the morning stretching, then it's within your arms. Why symmetries matter. One crucial concept underlies what has become the standard model of particle physics, symmetry. But it's largely down to the insight of one outstanding gifted mathematician, says Dave Goldberg. Okay, the standard model of physics, it has something we don't really understand it for yet. For now, it has something to do with 6 quarks and 6 leptons and then bosons and the Higgs boson. And they are all set inside of a fermion, they are inside of every atom, and that is how everything exists. And there's something symmetric, and this chapter is not about symmetry, whatever it is. The idea that symmetries lie at the heart of physical laws is old. Okay, for a long time people are saying all these physical laws, they have something to do with symmetry. What did Aristotle say to that? Aristotle and his contemporaries argued that the stars were pasted on celestial spheres and that the globes moved in circular orbits. They were wrong, as it happens. As Johannes Kepler discovered through meticulous observation in the early 17th century, planets wander closer and further from the Sun. In the geometric form of an ellipse. I actually want to know why. Okay, what we're telling is that Aristotle, so 2,500 years, I think, even ago, in the ancient Greek, thought there was the Sun, and all the planets were fixed on I think he said something about celestial spheres, whatever. He said they were fixed and they are always rotating in the same way. But now Johannes Kepler in the 17th century said no, they're not. Having always the same distance to the Sun, the planets, they are sometimes further away and sometimes further away. They are having an ellipse, so not a circle, but an ellipse. The Sun is in the winter closer to the Sun. The light is actually 2 seconds faster, I looked it up once. 2 seconds faster in the winter as it is in the summer. But I want to know why actually. No. They travel faster when closer in and slower when further out. Maybe that's okay, it's not the answer why it is an ellipse, but it makes a bit sense. If they are closer, they are faster. If they are further away, slower. It's actually very interesting. An imaginary line connecting planets to the Sun traces out equal areas in equal times. I don't understand the sentence. An imaginary line connecting planets to the Sun traces out equal areas in equal times. What we now know is conservation of angular momentum. I get it. If it is closer, it is faster, so that it is actually the same force onto the planet because it's faster away. And if it's further away, the distance is longer, but it is not a problem because it's slower, so whatever. I don't understand it. I think we're talking about something like that. The imaginary line traces out equal areas in equal time. They're faster when they're closer in, and for some reason that matches out so that it's always the same imaginary distance proportional to area and time they are a part of. I don't get it. I actually get it, but I can't explain it. But I'm not sure if what I get is the thing we should get. What we now know is conservation of angular momentum. It wasn't until later this century that Isaac Newton explained why this happens, with his universal law of gravitation. The source of his behavior was indeed a symmetry. The symmetry of the invisible hand of gravity, which acts equally in all directions from a massive body such as the Sun. Okay, Isaac Newton said something about the universal law of gravity that says that the gravitation is in all directions symmetric and always the same. And how does it happen on the planet circulating the Sun? An elliptic. Whatever. General relativity. Albert Einstein's much refined theory of gravity was founded on a symmetry too, one known as the equivalence principle. Okay, Albert Einstein wrote the equivalence principle, and that had something to do with symmetry. So it seems like whenever someone is thinking about how the world works, by saying it has something to do with symmetry. What was my idea to buy one of the quarks 70,000 times heavier than the other one? Was it based on symmetry? Not really. I don't know. This states that there is no practical difference between a body experiencing an acceleration because of gravity and one experiencing an equivalent acceleration from a different source, such as the thrust of a rocket or spin of a centrifuge. Let's read it again, because that sentence is understandable. This states the equivalence principle of Albert Einstein, that there is no practical difference between a body experiencing acceleration because of gravity. So the Earth travels faster if it's close to the Sun, and now it is too fast and gets catapulted, or whatever they call it. It gets thrown out of its circular movement because it's too fast when it's far away, but the gravity pulls it again in, and now it's too far away and the gravity pulls very strong, and now it comes almost in a straight line back to the Sun. Now it's very close to the Sun, it shoots a little bit forward, but now it's very close to the Sun, so it shoots not again to the other side, the same distance back, but only a little bit, because now it's very close to the Sun, and it has much momentum. It goes in a roundabout with the Sun. It's way too fast again because it was way too close, and it shoots it out way too far again. And now it's too far away. The gravitation is slow, the Earth is slower, but the gravitation gets held, it gets faster and faster and faster, and it's time to accelerate, and it does the same. And it's basically all the time doing that. That's why it's elliptical, because it's too fast and gets thrown out of its circular movement. Okay, this states that there's no practical difference between a body experiencing acceleration because of gravity and one experiencing an equivalent acceleration from a different source, such as thrust of a rocket. Okay, whatever, the acceleration everyone has the same experience. Whether we're sitting in a car and starting, whether we're running, whether we're sitting in a rocket or on a spinning planet, or we're sitting for some reason in a centrifuge. Now, from the equivalence principle, Einstein developed his theory that yields everything from curved space-time and an expanding universe to black holes and gravitational waves rippling through space. Now, from this principle that everything has the same acceleration, whether it's a little rocket starting or a big planet accelerating. Whatever Einstein thought next had something to do with that principle. All his theories to the curved space-time. That is the reason why it's curved space-time, at least the beginning of the theory. And an expanding universe to black holes. And gravitational waves rippling through space. Why do they ripple through space? Because they are gravitational waves. Are gravitational waves actually actual gravity? So we're not just like they consist out of something. Is a gravitational place? Is a gravitational wave a place where this space more gravity is than in another place? So here's more gravity and here not. And if the wave passes onward, then here's more gravity and so on. Where the wave is, there's more gravity. Why did I never had someone explain it, but this is a wave of gravity, but at the place where the wave is more gravity, because that's totally fascinating and understandable. And gravitational waves are totally fascinating with that idea. No, I don't know if it's true, but I think if it's not true, one could open my lecture with the first lesson with it. So when people come in and don't know it's not that. But it sounds logical. I don't know if it sounds logical, but I want to stay with that idea, even if the gravitational waves are not that. The idea that gravity, I don't know what causes them. Was it the Big Bang or Big Explosion, whatever. A gravitational wave is when the wave into that place there's more gravity. It's just normal water wave from the ocean is technically also a gravitational wave in that sense, man. Because at that place there's more water, because there's a wave, and now it has more gravity than the other parts. A gravitational wave is something passes through space, and at that place there's more gravity. How does it pass through space? Because of a curved space-time or what? Whatever. I find the idea very interesting, but when gravity is fixed to an object, a planet, a rock, but that it actually can move as nothing through space and time. Basically, through nothing can it move. Now we're ending on that. And if you hear from particle physics, whatever that noise, you can go directly to the next part. We're going to do now the morning stretching. If you participate in morning stretching, then it's very honest. Having a good and steady stand, and we're doing forward shoulder circles. Going back, up, in front, and down. And the last time. and then backwards. And now we're breathing in, lifting the shoulders up. And then breathe out, let the shoulders fall down. Again, in, lift the shoulders up. Then out, let them fall down. Again, in, the shoulders up. Now bring the upper bladder. Breathe in, lift the arms up. And we'll reach always high. Pretend to take an apple hanging high on the upper branch. Turn it around and to plant it. And breathe for the last ones, and then now doing a shifter. Arms to the side, we're breathing in. And out, we're shifting over to one side. And breathe again in. And out, we're going over to the other side. Breathe again in. Back in the middle. And out over to the other side. Breathe again in, one last round. And out over to the other side. Again in. And out, we're leaning onto our knees, the buffalo fighting its hangover. We're breathing in. And out, bringing one shoulder in front. Again in, shoulder back. And out, one shoulder in front. Again in, one shoulder back. And out, one shoulder in front. Again in, one shoulder back. And out, one shoulder in front. Up in. And out, and we're hanging down. Breathe in. And out with them over to one leg. Breathe in. Out over to the other leg. Breathe in. Out into the middle. And breathe in. And out, we're coming around back up and making it to the top and backwards. Now the garden pose. The torso pointing to the outside, breathing in all the space between the heels, breathing in, lifting the arms up. And breathe out, sitting down and pressing the elbows against the inside of the knees. And breathe in straight up the back. And breathe out and become back up. Breathe again in. And out again down. And in and straight up the back. And out we come back up. Again in. And out. Out again. Breathe in. And out we're coming slowly in one straight line upwards. Like the arms. And let's end with the eagle swings. The torso, the feet are standing together. They're breathing and lifting the arms up. And breathe out, the arms again down. Again in the arms up. And breathe out the arms again down. And last time, in the arms up. And breathe out the hands down. That was morning stretching. I thank you very much, and until next time.